Okay, so this is going to be a review of the acids, bases, and salts unit, and I will be looking for these notes on Tuesday morning of this coming week. So just to review, we've already talked about this on the pH scale, which goes from 1 to 14. 7 is neutral, so this would be water. Acids are less than 7, bases greater than 7. The further that you get away from 7, the stronger you are. So an acid with a pH of 1 is stronger than an acid with a pH of 6. Likewise, a base with a pH of 14 is going to be stronger than a base with a pH of 8. So let's review some characteristics. We already said their pH is less than 7. They are usually sour. They usually start with H. We talked about that the other day in class, and we get this from table K. They turn blue litmus red, and we've used litmus already. And some examples could be lemons, orange juice, vinegar, and tomato sauce, just to give you an idea. All right, let's talk about some characteristics of bases. Bases are usually bitter, and they usually feel slippery. They're usually a metal plus the OH minus ending, the hydroxide. They are found in table L. They turn red litmus blue. And some examples would be, well, actually, I want to give you another important indicator here. Phenolphthalein, and we're going to be using this like in the next week. Is pink in the presence of a base. And you can get that from looking at the indicator table. And it's clear in the presence of an acid. Some examples would be shampoo, dish soap, and I'm going to say various household cleaners. So before we go on, I want to explain something about the pH scale. I'm going to write numbers down here on the bottom. Every pH change is a 10-fold change in hydronium, which is in our polyatomic ion table, it's H3O plus, okay? But this is also indicative of H plus. So sometimes you'll see H3O plus or H plus. So what that means is, and let me explain this, if I go from a pH of 2 to a pH of 1, that is a tenfold increase. If I go from a pH of 4 to a pH of 2, that's 2 placeholders. So that's like 10 times 10. So this is a 100-fold increase. And if I went from a pH of 6 to a pH of 3, that's 3 pH changes. 10 times 10 times 10 is 1,000. Okay? Now, that's going toward acids. That's always going toward the left. So toward the left is an increase. If I go toward the right, it's a decrease. So if I go from a pH of 9 to a pH of 10, that is a tenfold decrease in a hydronium because you're becoming more basic. So remember, H is indicative of acid, right? OH minus is indicative of base. Think of it as a scale, okay? If this is my scale here, that's a bad drawing. Let's just say my OH, whoa, not the one I wanted. My OH was here and my H was here. This would be more basic. If it was reversed, so this is basic, if I had more H and less OH, then this would be acidic. When my H equals my OH, then it's neutral, or I have water. So how do I know when I have a salt? Salts are a little bit more difficult to recognize. Salts can be a metal and a halogen. So that's group 17. It can be a metal and a polyatomic, something from table E. Or it can be 2 polyatomics. So example might be NaCl or MgCl2. For a metal and a polyatomic, MgSO4. And maybe for 2 polyatomics, NH4NO3. That could be an example. Why am I bringing this up? Because acids, bases, and salts are electrolytes. And an electrolyte is something that can conduct electricity. And in order for something to be able to conduct electricity, it has to have mobile charge. Now, we already know that metals conduct electricity because they have mobile electrons. Acids, bases, and salts conduct electricity because they have mobile ions. For example, and you don't have to write this part, HCl, when I put that in water, it dissociates, or I'm just going to write it as HCl aqueous, make it easier, takes less room. So HCl aqueous dissociates into H plus and Cl minus. There's my mobile ions, charge. NaOH is a base. It's going to dissociate into Na plus and OH minus. There's my mobile charge. Salts, NaCl, aqueous, dissociates into Na plus and Cl minus. All of those have mobile charge, which makes them an electrolyte. Now, there's two theories of acids and bases. One is the Arrhenius theory of acids and bases, which basically says acids have H plus as the only positive ion in solution. Which makes sense because I just showed you that HCl dissociates into H plus and Cl minus. H2SO4 is going to be 2H plus SO4 2 minus. So they're always going to have H plus. And the Arrhenius theory of bases says that bases have OH minus as the only negative ion in solution, which I just showed you NaOH dissociates into Na plus and OH minus. All of your bases that end in OH are going to do that. The only one that's the exception is NH3, which doesn't even contain OH. So then that wouldn't even be considered an Arrhenius base because it doesn't have OH. And the reason why it's called the Arrhenius theory is just because of the guy that discovered it. Then we have what's called the Bronsted theory of acids and bases. Again, for the guy that discovered it. And on the reagents, it's never referred to by his name. It used to be. For the Arrhenius, it'll say, according to the Arrhenius theory, which one of the following is an Arrhenius acid? And you pick the one that has H plus. Or according to Arrhenius theory, which ion is the only positive ion in solution? H plus. But they used to refer to the Bronsted theory as the Bronsted theory. For some reason, now they refer to it as the alternate theory, or sometimes it's just referred to as the other theory, which I don't understand, but I don't write the reagents. So, according to this theory, acids are proton donors. And bases are proton acceptors. And I'll show you what that means. So if I had HF, hydrofluoric acid, plus H2O, and it formed H3O plus and F minus, you need to see what's happening in the equation. You can see that HF is giving an H to H2O because it becomes H3O. So this is considered a Bronsted acid because it is donating a proton. Well, you might say, Ms. Nielsen, it's not donating a proton, it's donating H. But if you look at H on your reference table, it only is one proton. It has no electrons. So it says acids are proton donors, so in theory it's saying H donors. An example of a base might be NH3 plus H2O yields NH4 plus OH minus. And in this case, you can see the H2O is donating to NH3. And the NH3 is accepting an H and becoming NH4. So NH3 is our base because it is the proton acceptor, which means, in theory, that water is acting like an acid here, in which it can. Water is a substance that's called amphoteric, which means that it can act as an acid or a base. Please don't write this. This is more like of an upper level concept. But if I have H2O plus H2O, it's basically going to form H3O plus OH minus. So what happens here is that one of the waters is donating H, so this is donating H, so this is my acid, and one is accepting H, so that is becoming my base, and when it does that, it forms H3O plus. So acids donate, bases accept. Okay, there are a special type of double replacement reaction in acid-base chemistry, and we've already talked about it. It's called neutralization. And it's when you have an acid plus a base, and it forms a salt and water. For example, HCl plus NaOH, we just did this in the solution chemistry lab, is going to form NaCl and H2O. This is a double replacement reaction because I have two compounds, HCl and NaOH, and they switched partners. The H hooked up with the OH to form HOH, which is water, and the Na hooked up with the Cl to form sodium chloride, salt. It doesn't matter. I could have HNO3 and KOH, which is a base. I'm going to form HOH, which is water, and now I'm going to form KNO3, which is the salt. Notice that water always forms. In every acid-base neutralization reaction, water is always a product. The salt will change, and it's dependent upon the acid and the base that hooked up. Now, another type of reaction that can occur, so this is double replacement, with acids and bases is what's called a single replacement reaction, in which we have an element in a compound, and that compound can sometimes be an acid. So here is what happens generically. X plus By. There's my element and my compound. X comes in and kicks B out, so it's by itself, and then X hooks up with Y. Now, does this occur all the time? No. It is dependent on one thing, and that one thing is table J. Table J is a reactivity table, and it has the most reactive elements on top and the least reactive on the bottom. So using a real example, Mg plus HCl. Mg has a +2 charge, H has a +1 charge. So positive can only kick out positive, negative can only kick out negative. But how do I know if something can get kicked out? I have to go to table J. The element pushing in has to be above the one that it's pushing out. So if you look at table J, Mg is above H. So it can kick H out. And when H is by itself, it's diatomic, so it's H2. And then the Mg hooks up with the Cl. But remember, this is +2, this is -1, so it's MgCl2. And this isn't balanced. I'd have to put a 2 here to balance it if we're really covering all the bases here. Okay, we're almost done. There's a special type of process in acid-base chemistry called titration. And that's using a known concentration and we refer to this as molarity. of an acid or a base to determine the concentration of an unknown. Whenever we use titration, we use the formula on table T, and it's called MAVA equals MBVB. And it tells you what each of the variables mean. Molarity of the acid times the volume of the acid equals molarity of the base times volume of the base. And this is the lab that we're going to be doing next. Another formula that we're going to be using from table T is the molarity formula, which says molarity equals moles of solute over liters of solution. Couple of things that you need to make sure that you're dealing with when you do these types of problems. You want to make sure you're starting with a balanced equation, if they give you one. And you have to make sure that your H to OH ratio is 1:1, or you have to make some accommodations in your formula. Last thing I'm going to do is a couple of practice problems, and that's it. Okay, so I'm going to review some of what we learned in some problems, and then we're going to do some more in class. So in 14, you don't have to write these, just listen and apply what we just went over. An aqueous solution turns litmus red. Turns litmus red. So if something turns litmus red, it has to be an acid. Now, if you couldn't remember that, you can see that 3 of these pHs are greater than 7, which would be indicative of a base. Only 1 is below 7. So there's your answer. If equal volumes of 0.1 molar NaOH and 0.1 molar HCl are mixed, the resulting solution will contain what? Well, one's an acid, it starts with H. One's a base, it's a metal and OH. So an acid and a base always produces a salt and water. It says it contains a salt, so the missing component would be water. If equal volumes of 0.1 molar NaOH and 0.1 molar H2SO4 are mixed, the resulting solution will contain water. And what else? So now they want you to find the salt. Well, you know that the OH is going to hook up with the H. OH and H, or H and OH, always hook up to make water. So what's left? The Na and the SO4. So NaSO4, how do you write that compound? Well, Na has a +1 charge. SO4 has a -2 charge. So when you drop and cross, it's Na2SO4. So you know that you have to have Na2SO4. Now, the reason why this problem is tricky, and it's not just Na2SO4, the answer is 1 Na2SO4 and H2SO4. This problem was hard because my H to OH ratio is not 1:1. I have 1 OH in NaOH, but I have 2 H's in H2SO4. And they said that they were mixed at equal volumes. So this is like a limiting reagent problem. I'm not going to use all of my H2SO4. A sample of a solution with a pH of 10 is tested separately with litmus and phenolphthalein. Okay, so now we go to our indicator table. You know it's a base. So now you just have to look at your indicator table and say, what color is litmus going to be when it's basic? You'll see it's going to be blue. And I told you that phenolphthalein is going to be pink. So the answer is 1. In 18, a student observes that an unknown solution conducts electricity, so it has to be either an acid, base, or salt. But it turns blue litmus red. Well, right there, the only thing that turns blue litmus red is an acid. An aqueous solution of an ionic compound turns red litmus blue. Right there, I should be thinking base. Conducts electricity and reacts with an acid to form a salt and water. So that confirms that it's a base. So they're looking for a base, and you know a base is a metal plus OH. Moving up to the other side, what will be the concentration of 150 mils of 2.4 molar NaOH if it's diluted to form 200 mils of solution? So this is kind of like an MAVA equals MBVB problem, which we haven't done any yet. This is a linking word. Whenever you see of, that of has to connect the two. So the 2.4 is going to go with the 150. That's a really bad color. Let me get a different color here. So the 2.4 is going to go with the 150, and that's going to equal X times 200. So this is like just simple math. You're going to do 2.4 times 150, and then you're going to divide by 200. And you're going to get 1.8. So X equals 1.8 molar. Both HNO3 and COOH can be classified as what? Well, this starts with an acid, and this can be rewritten. If you look in your reference table, table K, this is also written as H2C2, HC2H3O2, sorry. HC2H3O2. This is acetic acid. So they're both Arrhenius acids, and they turn blue litmus red. When the pH value of a solution is changed from 2 to 1, we talked about this, the concentration of hydronium. Whenever I go to the left, it increases, and it only moved one place value, so that's by a factor of 10. And here's that Bronsted-Lowry question. According to one acid-base theory, the reactant that donates H, so this donated H because this became NH4. So this was my donator, okay? That would be the H2O. 2 more questions. Which volume of 2 molar NaOH is needed to completely neutralize 24 milliliters of, there's the linking word, that tells you that these two go together. So we got 1 times 24, and that equals 2x. So 24 divided by 2x, x equals 12. Again, I don't have to make any adjustments here because my H to OH ratio is 1 to 1. In this one, though, I do have to make an adjustment. Sulfuric acid can be used to neutralize barium hydroxide. What is, oh no, this is not a neutralization, sorry. What is the formula of the salt produced? So look, H2SO4 and BaOH2. You know that H hooks up with OH. H hooks up with OH. That makes water. What's left? is Ba and SO4. Ba is +2, SO4 is -2, so they hook up in a 1-to-1 ratio, and that's my answer. All right, you didn't have to copy these. I just wanted you to follow along and apply what we learned in the notes, and I'll check for the notes on Tuesday.